Calculus was not made to be easy, it already is.
What's calculus?
Hey, BBQ Rambler here. This is my second video in a series on hit factor math and scoring. Today we'll do a hit factor deep dive. Topics include there's so much information to go over in this topic that I split the videos into A and B. Today's video A, and I'm going to warn you right up front, this entire video is a nerd alert.
Nerd alert!
For you guys. So if you're one of these, you might want to skip to these parts. Part A will be a lot of theory. Part B, when that comes out, will be a lot more colors and action and bouncing balls for, you know. Or check back to the channel for these upcoming videos. And speaking of, you guys watch this countdown for when bullets are going to fly again. This video will be very math graph heavy, and I'm going to move fast, so feel free to pause the video at any time and look what's on the screen. And if I do insult your intelligence a little bit, don't worry, that part's not for you, it's for... A lot of people were upset that my last hit factor calculus video did not actually have calculus in it. Nerds! So for you guys, I've actually put calculus in this video. So I know you're excited about that. Let's get started.
Hit factor is a simple equation, but the implications of the formula and how you improve your score are surprisingly complex. If accuracy and speed increase or decline by the same percentage, then hit factor will not change. So if you get 10% more accurate, but because you're trying to be accurate, you slow down and it takes you 10% longer in time, your hit factor doesn't change at all. So 10, still 10. Same thing the other way. If you go 10% faster, but it causes you to lose some points, 10% exactly, then again, your hit factor won't change. Notice that it's both of them going up means no hit factor change, or both of them going down. And why is that? If they both go up, that's a good thing for points, that's a bad thing for time. So if you do the equation, if they both go up by 10%, that 10% cancels out and you're back to where you started. Same thing the opposite direction. If they both go down, bad for points, good for time. 90% on each cancel out and your hit factor doesn't change. Now this is what you want. Points go up, time goes down. In that case you get 2 thumbs up, and we all want 2 thumbs up. So if points go up by 10%, time goes down by 10%, you have a 22% increase in hit factor. So you can see there's an exponential improvement here. This chart shows how much your percent change in points and percent change in time affects the percent change in hit factor. So up top we have the change in points, and on the left we have change in time. And the numbers in between are the percent improvement in hit factor. So the example we did before, 10% improvement in points and a 10% improvement in time, which is negative, leads to a 22% improvement in hit factor. Hit factor is directly proportional to points, and that's because points is in the numerator or the top of this equation. So whatever percentage of the total available points you shoot directly reduces your hit factor by that same percentage. You shoot 90% of the available points on that stage, you'll get 90% of the possible hit factor given that same time.
If you look at this, so if you're just improving your points and your time stays the same at 0% changed, the improvement in hit factor, which is here, exactly matches the improvement in points.
And how much each Charlie, Delta, Miss, etc., any non-alpha reduces your total points percentage depends on the number of points available on the stage. So time is irrelevant when it comes to percentage.
This is a simple stage with 2 steel targets and 3 paper for a total of 8 rounds.
There are 5 points available for every scored hit you get. So on an 8-round stage, that means there's 40 available target points. In this example, we'll use minor scoring since major is cheating. So if you get a Charlie, that's going to cost you 2 points because a Charlie's worth 3 and alpha's worth 5. So a Charlie basically means you lost 2 points that you could have gotten. With 40 possible points, that means losing 2 points is losing 5% of the available points. Here's a stage that has 100 possible target points, and there's only 4 targets, so I'll explain. So this is a classifier, can you count? And it has an unusual procedure, stage procedure, where you have 2 different strings. String 1, you engage the first target with 5 rounds, do a reload, engage the second target with 5 rounds. Then you stop, you reload, you do another string, 5 rounds in target 3, 5 rounds in target 4, and they add the time of the 2 strings together. So altogether, you've gotten 20 scored hits for a total possible 100 points. With 100 available points, Charlie still costs you 2 points, but you're only losing 2% of the possible points versus the 5% on a 40-point stage. And again, time is totally irrelevant. Here's a spreadsheet showing how much each non-alpha affects the hit factor on a percentage basis. So it starts at a 1-round stage, goes all the way down to a 32-round field course. And if you look at the example we did before, 8-round stage, 40 possible points on that stage. 1 Charlie will cost you 5%. And notice that minor and major have different percentages because minor and major cost you different amount of points for each non-alpha. So a 5% hit for a C in minor is only 2.5% hit for major. And as you go down the list, as there's more points available, 32-round field course, for example, your non-alpha hits are less detrimental to your score. So a Charlie is only 1.3% loss in minor and a 0.6% loss in major. You'll also see that with the smaller round count stages, it's possible to get 100% loss in hit factor because you're going to zero the stage.
You can download this chart at standingreload.com/videos. To recap, the percent drop in hit factor for each non-alpha depends just on how many points are available on the stage, and time is irrelevant. However, time does change how much each non-alpha affects the direct value of the hit factor, the actual number itself.
Hit factor is not directly proportional to time because time is in the denominator on the bottom here. So hit factor is inversely proportional to time. As time increases, so if you double your time, your hit factor is cut in half, inversely proportional. Here's another example. 10% increase in time pulls out to 0.91. Your hit factor goes down by 9%. And it goes the other way too. If you cut your time in half, it doubles your hit factor. So a 50% reduction in time leads to a 100% increase in hit factor. You get an exponential increase there because they're inversely proportional.
Now, if you do the same thing for time, it's not the same. So a 5% improvement in time, initially that's a 5% improvement in hit factor, but I bet, yep, it's actually 5.3. And as you go up The 40% change in time is a 67% improvement in hit factor. And it goes the same way if you're getting worse. So 50% slower is only a 33% reduction in hit factor. And this diagonal line shows when they match up. So 30% reduction in points, 30% reduction in time, the change in hit factor is 0. Anything to the left and below that is a reduction in hit factor. Anything to the right and above that is an improvement. The way to improve hit factor on a percentage basis is you either have to improve points or time without disturbing the other, or you improve one more than you're improving the other. So if you improve your points by 15% and it only hurts your time by 10%, you still end up at a 5% improvement in hit factor. Or starting from 0, 0, if your time improves by 15%, you can reduce your points by 5 or 10% and still have an improvement in hit factor. Let's look at how points and time affect hit factor when considered together, although to simplify it at first, we'll assume that one stays the same and the other one moves.
First, I'll talk about changes in points.
How much does increasing your points improve your hit factor?
The way you want to look at this graph is as if you ran the Can You Count classifier and you know that you got it done in 9 seconds, and now you have to go around and count up the points. So the difference in the points you scored will affect your hit factor greatly. So if you scored 0 points in 9 seconds, your hit factor will be 0. And if you scored 100 points in 9 seconds, your hit factor will be somewhere around 11. In between is a straight line, linear function. And that's a straight line because, broken record, points is in the numerator. It's directly proportional to hit factor. The next question is, how much does your hit factor increase for a given improvement in points? Before I get into calculating that, let's bring it back to something that's more normal that people deal with in their everyday lives. Let's say you and I are standing next to each other and you get in your car and you drive away in a straight line at some speed. This graph shows how far away you are from me after how much time. At point 0, or at time 0, we're standing right next to each other. After 1 hour, you're 100 miles away. After 2 hours, you're 200 miles away, and so on. Well, you must be driving 100 miles an hour, right? So how did you know that? Whether you realized it or not, you were taking the rise over the run, getting the slope of the line to figure that out. So 100 minus 0 is 100. 1 hour minus 0 is 1 hour. So 100 miles per hour is the velocity, the rate of change of your distance. And this is the formula for this line. This formula here will give you this line always and forever. So at hour 1, you can multiply it by 100 and you'll know right away that you're 100 miles away. No matter where you are in the time horizon, this 100 miles per hour is always the same because this is a straight line. This ratio of rise to run does not change. So if you made a graph of what the velocity was over time, it looks like this. Along the x-axis, it's the same as before. It's hours, 1 through 5. But now the y-axis, instead of being distance, notice it's delta distance or change in distance, meaning miles per hour. So change in distance is velocity. So across that time, at any point during that 5-hour drive, you were driving 100 miles an hour, meaning that the distance was changing at 100 miles per hour at every point along the drive. Or at each point along the x-axis, how much would distance increase if you increase your x-axis value, in this case it's hours, by 1? At this point at 2 hours, if you increased your time or if you waited 1 hour, 1 unit, the distance would change 100 miles. Now let's say there are 3 cars that drive away at 3 different speeds. is the same as before. Then you have this orange one, and you have a green car as well. So it's pretty obvious that over the same run, these lines have different rises. So the green line is shallower, the orange line is steeper, so the orange line has a higher rise for the same run. And if you look at them next to each other, it's very obvious. We can guesstimate about how fast each of these is going. So the green line after 1 hour, you're about 50 miles an hour. The blue one we already figured out is 100, and the orange one is about 150. And if we graph it and test, looks like that: 50, 100, 150. So the steeper the line is, the faster the rate of change. Since the slope of this blue line was 100 miles per hour, that means the formula for this line is y equals 100 times x. And this line was going 150 miles an hour, so 150 times x and 50 down here. So the number that's in front of the x in a linear function determines the slope. If y equals 100 times x, that means that the rate of change of y, or the delta y, is 100. Coming back to our original equation, points, hit factor on a 9-second stage. You complete it in 9 seconds. The formula for this equation is hit factor, or y, equals x over 9, which is 1/9 times x, which is 0.11x. So that means on this 9-second stage, or any 9-second stage, every point that you improve pushes your hit factor up by 0.11 hit factor. And that is why you have this graph. No matter where you are on the graph, on a 9-second stage, every point increases your hit factor by 0.11.
On shorter stages, each point that you get increases your hit factor by more than on longer stages, as shown here. Or another way to look at it is, as you get faster on the same stage, each point is worth more hit factor. Here's a spreadsheet showing time on the left. So this is the time it takes to get through the stage. And based on that time, how much each point will increase your hit factor. So we just did 9-second stage of any kind. Every point you get will increase your hit factor by 0.11 points per second. So if you shoot 1 alpha in 9 seconds, you'll get 0.56 hit factor. If you get 10 alphas in 9 seconds, that's a 5.6 hit factor. Here you have your minor and major Charlies and Deltas, because they're different. And then any of these hits will be negative. They'll reduce your hit factor. This spreadsheet, if you want to print it out, keep it in your range bag, will be available at standingreload.com/videos. There'll be a link to download the PDF. You can see that at lower stage times, there's a bigger impact on hit factor from each point. Down here, let's say 30 seconds, 1 point will only increase your hit factor by 0.03. An alpha is only 0.17 hit factor in that amount of time, 30 seconds. Down here at, say, 5 seconds, an alpha is 1 whole hit factor. Now we'll look at changes in time. How much does reducing your time improve your hit factor?
This graph shows a fixed 90 points and varying time. So if you score 90 points on a stage and you look at it at the end and you finished in 16.5 seconds, your hit factor will be a little over 5. If you finished in 5.5 seconds, your hit factor will be over 16.5 or so. In between those two extremes is an exponential function. Now technically this is an exponentially decreasing function, but I'm going to look at it going this direction. So as you improve, you get faster. Your goal is to get faster, meaning your time gets lower and your hit factor goes up. So instead of looking at it this direction, the typical direction on a graph, I'm looking at it right to left. The reason this graph looks like this, it's not a straight line like before, is because hit factor is inversely proportional to time. Time is on the bottom. So that creates this exponential shape. And that shape affects the measurement of the rate of change of hit factor. So if you start here at 16 seconds and you improve to about 15 seconds, so you cut a second off your time, your hit factor will improve by this much. However, if you start up here at about 8 seconds and you knock your time down to 7, your hit factor improves quite a bit more. Big difference there. Time saved at this part of the graph is not as valuable as the same amount of time saved at this part of the graph, albeit saving time when you're at this part of the graph is much harder than if you're up here. The way you figure out the slope of the line is by looking at the tangent. So the tangent is if you're plodding along and right here, what is the slope right at this exact point? Here's the line, and it looks kind of curved, but that's an optical illusion. You can see that actually it is not curved, it's a straight line. So at that exact point, the tangent of the blue line tells you what the slope is, and you can see that the slope is steeper here than it is down here, meaning that the hit factor improvement is much higher here than it was over here. So we can't actually measure to the blue line like we did before because the slope is different up here. We have to measure it to the tangent of the line. One way to figure out what the rate of change is at every point in this line would be to draw a line on the screen and do this analysis for every point on the line, but that is not efficient and not very accurate either. Another way to do it is what you've all been waiting for: calculus. So the formula for this line is y, or f of x, fancy word for y, is 90 over x. So we can figure out the formula for the slope of that line, the 90 over x line, by taking the first derivative. And it results in minus 90 over x squared. And for those who want to see the math, there you go. That's the rules that were used. Here's a graph of the negative 90 over x squared, which is the delta hit factor. So this is how much hit factor is changing at every point in time. And it looks kind of weird, right? It's negative, it's showing minus when actually hit factor is getting better. Why is that? That is because the correct way to look at this graph is the original graph, seconds hit factor, is left to right. So left to right, the slope is going down, which means it's negative. And over here, it's less negative than it was up here, so it's getting closer to 0. Which is why it's very negative here, and it gets less and less negative as it goes on. I don't like looking at it that way though, so I took some creative license and I did the absolute value of that function to get 90 over x squared. This better represents the way that I'm looking at it, which is you're starting here. As your time gets lower and lower, your hit factor goes up, or your rate of change of the hit factor goes up in this case. Let's take a look at this graph and how we read this. If you are shooting the stage in 13.5 seconds, this says your rate of change of hit factor is 0.5. So that means at this point on the original graph, every second you improve, you're going to improve your hit factor by 0.5 hit factor. Down here at 9.5 seconds, 1 second improvement or 1 second reduction improves your hit factor by 1 full hit factor, 1 full point per second. Down here around 6.5, you're looking at 2 hit factor improvement for every 1 second of improvement. So as you get lower and lower, smaller time, your hit factor is improving exponentially more than when you were up here. Let's compare that to our estimates before. Let's see what it really is. So this is the graph that will tell us at the same points. The change in hit factor up here is 1.41. And up here at 16, we have a 0.35 hit factor if you take it across to the rate of change.
Now we'll look at points in time changing together.
Here's a spreadsheet showing points, time, and hit factor all together. So you have points on the bottom, time on the left side, and the number in the middle is a hit factor. For example, if you score 80 points and it takes you 10 seconds where they meet, 8.0 is the hit factor.
And for those of you who have trouble visualizing this,
here's that same information in graph form. Target points are here, time is along the bottom, and the height of each bar is the hit factor. As the points go up, the hit factor increases, and as time goes down, hit factor increases exponentially. With this graph, it's very obvious how at lower time, your improvement in hit factor is bigger. So here at 17.5, you'll increase your hit factor, but not that much. Here at 10 seconds, it's much more, and down at 5.5, it's significantly more. Looking at that on a graph, every target point you improve on the stage will improve your hit factor on all of these, but at 17.5 seconds, it's less, it's slower than 5.5. And this is what it looks like as far as rate of change. At 17.5 seconds, every point gains you about 0.06 hit factor. At 10.5 seconds, it's 0.9. At 5.5, you're over 0.18. And you have the same situation on the time side. So if you're only scoring 60 points on the stage, you'll get gains by improving your time, reducing your time. But up here at 100 points, you'll really get gains by reducing your time. And this is what that looks like. You can see that the 100 is steeper than the others and higher improvement. And there's the rate of change. If you're on a stage and you end up here, that's about 70 points in 10.5 seconds. And you want to get up to here, you're going to have to improve your points up to about 90 and reduce your time down to 6.5. And by doing both of those things, improving both of those things, your hit factor will improve drastically.
here's a recap of the main points. To improve your hit factor, you either have to improve your points or your time while the other one stays the same, or improve one at a higher percentage than the other one gets hurt. Improving points leads to a linear hit factor increase, while improving time leads to an exponential increase. Now, just a side note, this doesn't necessarily mean that improving time is more important than improving points. I'll have a whole other video just on that topic. And finally, hit factor increases more as you get to higher points levels or lower time. In the next video, Hit Factor Deep Dive Part B, I'll analyze hit factor changes during the stage instead of looking at it after.
Here's a chart showing how much your Yes.